turn. As I know, I'm sorry for this disruption at the beginning. I started saying that Mirna is the alma mater of this international conference that brings together scientists, intellectuals, artists to rethink the world after the COVID-19. Mirna is a reference in the field of mathematics and logic. She is a professor at the University of East Anglia and Sorbonne. She is a CEO of Logique, author of Théorie des Ensembles pour les philosophes, and she's a committed scientist and intellectual. My blood unites me to her, and she was a youngster. She was breaking the glass ceiling in the science because of her professional excellence. But this excellence is manifesting in many cases in the personal way. So it's a great pleasure to have you here talking about what very abstract mathematics has to show to the world.
Thank you so much, Esma, for this very warm introduction, and the feelings are shared. Thank you. It's a great pleasure to have you here, and thank you to everybody who has come to this talk. So my talk will be structured about something that is very abstract, but I'm going to present it in a way that I hope everybody can follow. That is the idea. And then we are going to make some conclusions. So this is my title. What does very abstract mathematics have to show to the world? And now I have to just find a way how to, something seems to be stuck with my slides. So please just give me 1 second to deal with that. Okay, so what is very abstract mathematics? What does that mean? So let us say that mathematics, most people would agree with this, is supposed to be based on some basis. Somehow we have a reason to believe mathematics, and this basis, as undefined as it might be in the minds of most people, including mathematicians, is what we call the foundations of mathematics. Foundations of mathematics try to encapsulate the common truths that, combined with complex arguments, then give us what we call mathematics. So I call these complex arguments mathematical wizardry. And this is what more especially is called deduction. So this wizardry gives rise to the whole of mathematics, basing on these foundations. So when we hear that something has been mathematically proved, what we really mean is that there is an argument that has been found using a deduction, and this deduction was made from the basic mathematical principles, and we have succeeded to prove the statement in question. So to understand this idea of foundations of mathematics, we go to the idea of mathematical logic. So we use means of mathematical logic. And this mathematical logic, for some reason that is strange to me, are rather rarely taught. And therefore they are considered to be very abstract, so abstract that when speaking of such mathematics, people would use this idea of very abstract mathematics. So my talk today will try to bring some very abstract mathematics in this sense closer to you. And I hope that I will try to prove I will succeed in proving my points that this is not all that complicated. So what is logic? There are many answers to what logic might be. So 2 explanations of what logic is, I think both equally lacking in depth. There is an American rapper called Logic, so I think for some people probably that is what logic means. More commonly, logic is associated to a single mode of thinking that was formulated using the principles of the ancient Greeks, who named this process logica. There is an accent missing on this mu, but I don't know how to put it on. But here's Socrates. So we tend to say logic was invented by the old Greeks. I personally believe that logic is something that is inside of every human being. It didn't need to be invented by the old Greeks. But what is certainly true that the way that we do mathematics today comes from this way of doing mathematical logic. So this is why it is called logic, and this is what we do. So now, today, what does logic mean? So logic today means basically the study of some basis of some reasoning. So the basis is made so to fit to the reasoning you are interested in studying. It could be mathematical reasoning, it could be philosophical reasoning, computational or everyday reasoning. It could also be reasoning in natural languages. So logic appears in many contexts, and mathematical logic is a branch of logic that studies reasoning in mathematics. And among other parts, it includes the subject of set theory, which will be the subject that I will talk about today. So what's set theory? It was discovered in the 19th century for purely mathematical reasons. That is, George Cantor was trying to solve a problem in analysis, and he came up with this theory that is called set theory. So it was not discovered or invented, as you wish, depending on your philosophical preference, for reasons that today we would call logic. But it actually entered very quickly into the context of logic because it was integrated in the program by the 19th century and early 20th century mathematicians led by David Hilbert, who wanted to find a unique foundation of all mathematics. So they have wanted to find the principles from which all the rest of mathematics can be concluded using deduction. So in this talk, we are going to do some modeling. So Dimitrios Papageorgiou was talking about modeling and some positive direction of modeling, what can be modeled, how we can use mathematical modeling to model COVID. After his talk, we had a talk by Jean-Marc van den Broek, who warned us about some limits of mathematical modeling. But we are going to do some modeling, which is perhaps a bit less usual. I will come back to what we actually mean by mathematical modeling in general. So we'll try to test the powers of mathematical logic and set theory to make conclusions about society. So why would this be a reasonable proposal? Well, it actually is a logical conclusion, because if we believe that sciences largely, and including the present understanding of social sciences, are based on mathematical truths, and if mathematics is based on mathematical logic, then we could use mathematical logic to draw conclusions about the society. This seems like a reasonable thing. So our thesis that we are going to try to defend during this talk is that even though mathematical modeling cannot help in modeling irrational behavior, as was mentioned and demonstrated in Van den Broek's talk and others, it can help in recognizing when a behavior is irrational or contradictory. And this is especially true of modeling using logic. So what I have in mind is a modeling which will tell us, look, what you're doing cannot possibly work. This is not reasonable. And I'm going to express that in a very specific example. But let me first say how mathematics has been used in modeling and what kinds of modeling we have in mathematics. So first, I will mention the modeling using continuous mathematics. This is done by some differential equations where the medium is supposed to be continuous. Things are happening continuously, so we can write some differential equations, partial differential equations, as they were mentioned in this SIR model and other models that were shown in Giorgio's talk and some other talks. Then one kind of modeling, which was mentioned only in passing in some comments, is modeling using discrete mathematics. So discrete mathematics doesn't assume that you are dealing with a continuous medium. Rather, it assumes that you have some points, sets of discretely distributed objects. And two kinds of things that people have studied in this context are graphs and games. There are other parts that are studied in discrete mathematics. But I should like to mention that even though there is no Nobel Prize for mathematics, there are at least two Nobel Prizes in economics that were given to people working in this kind of mathematical modeling. And I have in mind Robert Aumann and John Nash. There is also a very influential work of mathematical modeling using all kinds of mathematics, including discrete mathematics and game theory, which was done by John von Neumann, who was certainly a genius. And I use this word genius dérapé because at some point of his life, he took his mathematics too far. And this led him to a disastrous engagement in aggressive advice to the US after-war government, including the advice to throw the nuclear bombs, since otherwise the enemy will throw one on us. And then I will come to the part of modeling which is most relevant to what I have to say. It's modeling using logic. So logic is used to model artificial intelligence. It's used to model data sciences and many other modern aspects of mathematics. And I will be modeling using set theory, which is not something that is quite as usual as modeling using games or using partial differential equations. It is something though which has already been done. There is a celebrated French philosopher, Alain Badiou, who has admirers, who has also some critiques, and who has used set theory to model many everyday situations, everyday or not so everyday situations. So he has pushed this idea very far. I will be very concrete. I will have a much modest goal than that of Badiou, and the links to mathematics in what I want to do will be quite specific. So what is it that I would like to show today? I want to concentrate on showing one very specific thing. I want to show the irrationality of a certain political position that I claim is clearly immoral, but is also totally irrational. And this approach has actually already been done by some great people in the past. I will take one example. You have here a photograph of a page, first page of the Réflexions sur l'esclavage des nègres. In fact, it was the French mathematician Condorcet who wrote in 1781 a book about the immorality of slavery, which was then present in the Western societies. He argued about it on moral terms. And I warn everybody in the audience, what was considered moral terms at the time was certainly much more moral than the Traité de Nègre, which was used up to that point, but is not at all what we would today say are moral terms. So there are some things that we would consider immoral, but it was certainly very moral for the time. But him and the others did not succeed in achieving abolishment of slavery by the moral arguments. And then he got involved in the French politics during the Revolution, and he succeeded to push the abolition of slavery in 1794. not on moral terms, but on mathematical, economical terms. That is, he just convinced the assembly that slavery is not economically viable. Even though he had the moral argument, the argument that won the final battle was a mathematical argument. So I would like to do the same with something that I believe is immoral. So what I would like to show is that logic implies that having one single political system in the whole world is not reasonable. The world's attempts so far to construct such a system have also been immoral, since many people around the world have lost their lives in various attempts by others to democratize them. These attempts have been a guise for the colonial and neo-colonial politics. I want to claim that in addition of this being immoral, it is also unreasonable, since we have a mathematical prediction that such a uniformity cannot be achieved. So let me then, now that I hope that I motivated you somewhat, teach you some basics of set theory, because that's what we are going to use to demonstrate this thesis. Set theory is based on the notion of membership. If you were watching the blackboard or whiteboard that was behind Philip's back as he was giving his talk, you will have noticed this symbol here. This is the symbol of membership. This symbol is the basic symbol in set theory, and it's applied to the abstract idea of a set. So what's a set? It's not something to define. It is understood as an assembly of objects which is totally determined by its members. We don't define what a set is, just like in geometry, we do not define what a point is. And we write A is in B to say that the set A belongs to the set B. And it turns out that this very simple relation models many notions in mathematics. For example, we can talk about the set of natural numbers or the set of all real numbers. Natural numbers are 1, 2, 3, etc. Real numbers are probably all the numbers that you know if you are not a mathematician. And if you are, then you know what the definition of real numbers are. So all the numbers possible. Or also we can talk about the set of solutions of some simple equations, such as linear equation x plus 3 is equal to 5, or a set of solutions of some complicated equations, such as this extremely complicated equation called Navier-Stokes equation, which was mentioned by Papa Giorgio in the context of modeling the spread of drops when sneezing. So set theory can model many things, and because of that, it has gained much recognition as a good foundation of mathematics. But in order to do something with these very simple objects and this very simple relation, we actually have to make some assumptions. And these assumptions are called axioms of set theory. So even though the basic notion of set is quite simple, we can't get very far unless we assume something about it. For example, in geometry, just if we say this is a line, this is a point, and if we do not say anything more, then we are not going to have much knowledge about constructing geometry. So the same is true about the sets. We have to make some assumptions. So for example, in geometry, we assume that through every 2 points, there is a line. In set theory, we have some other assumptions which are more complicated to state at this kind of talk. But at any rate, it's similar idea. This kind of assumption is called an axiom. And collecting all these axioms in one list, we get what is called axiomatization. And you will not be surprised, there isn't a unique axiomatization of set theory, but the one that is mainstream and studied the most is called Zermelo-Frankel with choice, and it's denoted by ZFC. So this is what we will understand now by set theory. But you might replace this by your favorite axiomatization if you are into that kind of thing. And now we have these objects. We have some conclusions about, some assumptions about these objects. Now we would like to make conclusions. So what do you use to make conclusions out of your assumptions? You use logic. So in mathematics, this is all very defined. Conclusions in mathematics are made starting from the axioms and using a fixed method of deduction. So what's a deduction is basically the same what's a logic. So you can say you have some fixed logic and you are deducing further statements from the ones that you are assuming. I should like to say that there are more than one logic. This has come through our talks. We have, for example, in Anna's talk mentioned that there is a non-standard logic, or what people called it in his talk, I don't remember, but there are logics which are quite different, and studying these abstract logics is a very interesting field of mathematics. But I will give you two very simple examples of what logic would be. For example, we have a logic of propositions. So this is the simplest ones. If I know that A and B are true, then I can conclude that the compound statement A and B is also true. So this logic was studied by Aristotle. Or we have a more complicated logic, which is the so-called first order logic, which in addition to the propositions also includes expressions of the type there exists an X such that some property phi holds of X. For example, there exists the smallest natural number. And of course, we know this is a true statement. So this is an X. This X is the smallest number. The property is being the smallest. And with the real numbers, there is no smallest number. So we have expressions of that type. And in the Western Europe, this was first studied by Frege in the late 19th century. But in fact, later research have shown, research by Wilfred Hodges, above all, has shown that this kind of propositions were already known to Avicenna in the 11th century. So the Arabophone mathematician Avicenna from Uzbekistan. Anyway, to come back to us, ZFC set theory is based on first order logic. So that's the logic we need. Now we have everything. We have sets, we have axioms, we have logic, and we can make conclusions. And so now the idea of this Hilbert program is that we should, using this kind of thinking, be able to give a uniform foundations to all the mathematics. It was a very noble try. So his program was from the late 19th century to give a uniform foundations to all of mathematics, so that we should actually be sure of our conclusions. The motivation was that we really want to be sure that what we say is right, because it has turned out that some statements in mathematics actually turned out to be in some sort of a gray zone, and nobody knew if it was actually true or not. So the way that this connected with set theory is through the work of Hilbert, who looked at George Cantor. Here is a typo, this should be a C. George Cantor's set theory was the framework that was proposed by Hilbert. So 19th century was the time when people really wanted to be sure, and they believed they could be. And I can mention this book, World of Yesterday, which is one of my favorite books, written by Stefan Zweig, in which there is a part about the 19th century, in which he calls the 19th century the century of insurance and being sure. So in this way of thinking, we can also view Hilbert's program as wanting to have this assurance that what we're doing is true. Now I'm going to mention some other great thinkers. I will mention the great Spinoza. Spinoza has taught that universal democracy and international collaborations are the paths to the everlasting peace. So there is this word universal, which is happening here. And the point is, can we have such a democracy? Now, from the point of view of set theory, the big news came in the 1930s because Kurt Gödel proved that set theory cannot be the basis of every thought in mathematics. Moreover, he proved that nothing basically can be universal foundation of all of mathematics. So however you change this, you change your sets, you call them categories, you change them to something else. If you do whatever is by the standards of our thinking considered reasonable, there will be statements that you will not be able to prove or disprove. This is what's called incompleteness theorems of Kurt Gödel. And well, many people, I must say, completely ignored that Kurt Gödel was doing this. In mathematics, I think they might have considered this to be somewhat esoteric and not interesting. But another shock came in 1963 because there was a very concrete example that came to show in a concrete way, by a concrete simple statement, that Gödel was right. That is, there was a statement that mathematicians didn't know if it was true or not since the time of Cantor in 1878, and in 1963 it was proved that we cannot know. So let me tell you this statement, and I'm sure you can explain this statement to anybody who is at least 10 years old. So first, let me talk about the idea of bijection. So two sets are in bijection if there is some function from one of these sets to another which associates exactly one element of the second set to the first and vice versa. So if I have two sets of three fingers, I can put them together in a bijection. So now every element of the first set, which is my right hand, is uniquely connected with an element and only one of the left hand. Or if you ask children to count, this is what they actually will do. If you ask a child, how many apples do you see in front of you? The child is likely to count them using his fingers, and he will say 3 because he can make a bijection. And the idea of bijection is very important in Cantor's thinking because this is the way that he has found to estimate the size of infinite sets, not finite sets that have 5 or 10 elements, but infinite sets. And he has made some very important research on infinity. And one thing that he has shown, that if you take those two sets that we mentioned before, the set of all natural numbers, call it n, and the set of all real numbers, r. So remember n, it's 1, 2, 3, and so on. And r is all the numbers. That there is no bijection between the two of them. Even though there are both infinite, there is no bijection. So we have two different infinities. And then he made the continuum hypothesis. This is the continuum hypothesis, the way that we understand it in set theory. And I think Jean-Marc will make an interesting comment about this after my talk. You remember there was a different continuum hypothesis in Papa George's talk, Dimitrius's talk. So anyway, the one that Cantor formulated is that every infinite set of numbers is in bijection with n or with r. So there is no third infinity. There are only these two among the sets of numbers. And he tried to prove this. Very embarrassingly, he published some footnote in some paper saying that he can prove it and that he will do it. Then he realized he couldn't. He worked on it for 30 years. Cantor unfortunately got mental disease at the end of his life, and it is not impossible that this sad fact was connected with the fact that he couldn't solve this problem. But in fact, the reason that he couldn't solve this problem became clear in 1963 because combining the work of Gödel from the 30s and the work of Paul Cohen in 1963, it was shown that ZFC set theory cannot prove or disapprove CH. So if we believe that set theory is the foundation of mathematics, it should be able to answer all questions in mathematics. And here is this one statement that it cannot answer. And as I said, I'm talking about set theory because this is a well-known example, but nothing would change if you change set theory by something else. Still, there would be something that you cannot prove or disapprove. So this is quite a shocking piece of news. It was taken as a shocking piece of news by many mathematicians, and many mathematicians stopped working in set theory at that point because they said, this is too esoteric for me. Let me work in finite number theory. It's more sure. But for those of us who have done set theory for our life, this is simply that we have learned how to live with the plurality of models of set theory, of ZFC. We have a model, all the axioms are true in this model, and then maybe CH is true in that model, but we might have another model and CH is not true. And fourth, it is obvious that the global truth does not exist. I should say that there are people in set theory who are trying to find ultimate axioms. I'm not thinking of that. It would be an interesting discovery, which I do not think will happen. For me, the reality is, at least the one that is known now, is perceived by the multitude of the universes of set theory. And this is an attitude that is called pluralism. We have a plurality of connecting universes that communicate to each other within some basic knowledge, but then some know more on some subject than the others, etc. So if we believe that logic is a foundation for mathematics, and that mathematics is a foundation for science, and that science is a foundation for the understanding of the society, then what can we conclude? We can conclude that there is no universal democracy. And the word the universal is what I want to emphasize. Democracy comes in versions, and there is nothing that we can call universal democracy. Here you have a picture of Aristotle. He has already warned that the Greek version of democracy is not the perfect system, but that it was the best known to him. This is what he said. Clearly, a man of his talent could not omit to notice that the system in which neither slaves nor women nor metek have the right to vote is not an ideal one. And what we humbly suggest is that the system in which some powers, so one big power, push their version of democracy to the others is not only immoral, but it is also mathematically unsustainable. It is mathematically unsustainable to think that there is one fit for all democracy. Giving up the universal democracy of Spinoza, we don't have to give up the whole noble thought that he had. We do not have to give up the international cooperation. Solidarity and international cooperation, to me, seem to be the only reasonable way forward. This is what was started by the movement of non-aligned countries in the 1960s. This is why there is a street in Delhi named by Marshal Tito, because this movement was started by Yugoslavia and India, among other countries. And I think that this kind of international cooperation and solidarity will happen when movements such as Swaraj, that we heard in this brilliant talk by Yogendra Yadav, will gain an international visibility. So that's what I think. And I hope that COVID is this crisis that we have all lived, in which there wasn't any discrimination against, well, there was some discrimination, but the rich and the poor were affected by the COVID, will make us think of solidarity. And let me finish this talk by saying that this was a general introduction, after which logicians, of which many are in the audience, can ask many questions. I have written much mathematical and philosophical work on pluralism, where more detailed arguments are available, but I do not think that they are appropriate for this talk. And also let me say that some of you have asked me, what is this Logique Consult? So Logique Consult is my personal way to take logic out of its box, as I've done in this talk. I have spent all my life doing logic. This is the love of my life. And I, thanks to being able to climb through the university system, became a full professor at a distinguished university. And after a while, I've realized that being in the current day university system, in the kind of university where I was employed, was putting me in a box where I didn't want to be. So I have got out of the box, and I will be stepping down of my full professorship at the end of the month of August, and I will be fully employed in my own personal company called Logique Consult, which exists since 2014, and whose job is to take logic out of its box by teaching it in different ways to people who perhaps wouldn't have known it before. For example, this African Institute of Mathematical Sciences, where Rehanna is now working. I was there too, by researching in logic on the subjects that I want to research, that I find interesting, and so forth. So that is my Solidarity adventure for the time to come. And thank you very much for your attention to my talk.
Thanks so much, Mirna, for this very applying in share of possibilities, especially these people you're talking about relative models. So we are going to open the debate, but I just want to ask you a question. This is the point of view of humanistic research. What about when you have another option? But when pose just a one, we're talking about that there are no perfect models. But when we are proposed just one model, what can?
Unfortunately, your internet is breaking. Is there anybody who could hear this question?
Sorry.
There is some echo and I didn't understand. Yeah, can you write your question on the chat maybe, Esma?
I think too many people have their mic on.
Okay, Georg. Let's see. Right now it is just Esma and me and you. Yes, Esma, what was this question? Can you say?
I'm just reflecting on the way of having kind of models in our society, because in the last years, in last decades, we are in a way of just one model that we are losing about.
Yes, this was exactly the point that I was trying to make. I think that there is no one model. I do not think that we can have a society in which there is one single model that fits all. I do not say that there isn't a common intersection. There is the morality, but there cannot be a common model that will fit all the societies. And certainly, I do not think that it should be a defined model, and it shouldn't be brought as a definition from somebody else. I will read the question that has, if you don't mind, Esma, because you have some problems with the internet. I will read the question that came from Giselle. She says, thank you for the conclusion of this talk. The democracy that wants to be imposed by the Western powers as the best system, doesn't it also reach, goes against its history with the risk? Isn't it risky to give up the democracy because there will be some totalitarianism? Well, I think as the example of the United States shows, there is unfortunately possibility to introduce totalitarianism also in societies which are nominally democratic. I would like to mention to you an anecdote about Kurt Gödel. Kurt Gödel escaped Austria of the Second World War and went to live in Princeton. And after some time, he became a candidate for the US citizenship. And he very studiously studied the laws that he was supposed to know. And he realized logically that these laws do not prevent the existence of a totalitarian system in the United States. And he was very eager to say this during his interview for the citizenship, because he felt that this was very important. Yes, and his friends, including Albert Einstein, tried to convince him that perhaps this wasn't the best occasion. Anyway, for Gödel, there was a happy end. He got his citizenship. The officer to whom he explained the logic probably didn't pay much attention. But now we see Kurt Gödel was right. This is the second time that we are seeing that this man could predict very concrete situations using very abstract thinking. So yes, I think totalitarianism is not a good system, but I do not think that the present definition of democracy, as Giselle mentions, is something that's going to prevent totalitarianism. Anders, you seem to have a question.
But I think Jean-Marc has a question before. Jean-Marc.
Yes, Jean-Marc.
There is a...
Can you hear me?
Yes.
Yes.
I wanted to make a short comment about the continuum hypothesis. We heard one version of it in Dimitrios Papageorgiou's talk, and we hear now in Mirna's talk the concept of continuum hypothesis in logic. And they, of course, if you look, it's the same name, but it's something which is completely different, at least when you look first at it. In fluid mechanics, in Dimitrios' talk, we want to model fluids, and of course, fluids, there's a lot of molecules, a huge number of molecules, but you could even look at it as being infinite, but it still is still a countable set. In fact, it's something like what Mirna called N, the set of natural number. And on that, you cannot do anything. You cannot do much because you can talk about the velocity of each molecules. But what you want to do is to get a velocity field, something that you can differentiate so that you can write a differential equation. So the continuous hypothesis is to move from that countable set to, in fact, a subset of the real, or a subset of R3 if we want to model fluids in 3 dimensions. So again, there are also, I wanted to say here, it's interesting to see that in the continuum hypothesis of physics, of fluid mechanics, of continuum mechanics, we also have, it's also deal with infinite sets. In fact, the situation is, as Dimitrios mentioned, you end up with a Navier-Stokes equation. Usually you cannot solve them. You cannot write down the solution. So you have to go and try to find some numerical approximation on the computer. And then you go again from the continuum to some kind of a discrete system. And the discrete system is that you don't go back to something like the integers, but you go back to the rational. This will be defined.
Excellent, Jean-Marc. It's really a very interesting comment, but maybe you could stop after 5 minutes. Could you?
Okay, then I will ask you a question. You show mathematically that universal democracy is not possible, and I certainly would agree with you based on intuition. But you talk also about infinite sets. What about if we take into account the fact that there is only a finite number of people on the planet and a finite number of countries?
Oh, bravo, Jean-Marc. This is exactly what I wanted as a question. So I'm going to take a leaf out of your book. In applied mathematics, of course, everything is finite. But very often in applied mathematics, you will see papers that say, let us work with water of infinite depth. What infinite really means is a very large number. So infinite is used in mathematical modeling to measure numbers that are much larger than the other things that we consider. So if we take that line of thinking, then we can think of some large country as the United States, for example, which has a huge number of people, as infinite compared to an individual. So that's where the infinite sets come in. So you can think of the way that I think of this, these countries are like models of set theory.
Yes, that's a very interesting point. You should communicate that to Donald Trump, because that's the problem of immigration. He wants to put a wall so that you don't have any more immigrants. But if it's an infinite number of people, then you
can let all the immigrants
coming, you still have the same cardinality.
Yes, yes. Well,
put
that's
that
a very good point.
Twitter.
Indeed. Well, okay. Let Andres ask his question.
Well, first of all, let me begin by saying that I really, like and really side with your conclusion about pluralism and pluralism in political systems and pluralism in human endeavors. And I like the way you thread it all the way from, from the many universes we have, through forcing, and then through mathematics all the way down to society. However, let me just say, yesterday I mentioned this Giancarlo Rota question of what is the logic of Fundierung. So of course it's a technical thing, but part of what it refers to is how one branch of knowledge is founded or is encroached into some other branch of knowledge, so to speak. It can be an extremely simple thing, like the color blue is always somehow in space. That's a very simple thing, but it is also like what you were saying, the way mathematics is founded in set theory, or the way set theory is founded in first order logic, or the way you even shift these logics to to many other logics, as we know, that give even more plurality, richer plurality than in set theory. The problem is the way you link one level to another, because sometimes it's not a one-to-one linking. Sometimes you may have plurality in one level and may somehow lose it. I mean, you have to explain why the plurality is inherited from one level to another. And when there were these examples, of course, many people said, yeah, but we never found this sort of examples in mathematics and so on. And then later on, we found, oh no, even in combinatorics, we find examples that might actually be, this sort of plurality. So it's just a side comment. We now need to study much better, not only how things are based in logic, but what is the internal logic of how the world is based on mathematics and how mathematics is based on set theory and so on. And that's a very difficult task for us. But
I totally agree with you on this. This is not a win-win situation. It is something that can be studied. I've started writing a paper in which I explain how the axioms of set theory can be understood in everyday terms. Of course, we know that set theory and the axioms of set theory are not sufficiently strong to even describe the world of mathematics. We have other foundations. Sure. Yesterday we talked about category theory, etc. I think the point that I was trying to make is exactly that humble statement that if we cannot even control our own thoughts, our own inventions or discoveries, which is mathematics, how can we possibly think that we can have a universal recipe that is going to control the world of everybody on the planet? I think this is just completely preposterous.
Yeah, no, that's
preposterous.
Another comment, Mr. Menachem. Okay.
No, this is from Fernando. Menahem is gone, I think. Menahem said that he had to go. I think there is Fernando Zalamea now.
No, I just wanted to thank you again, Mirna, for your beautiful ideas, your thought, and especially what you are announcing to us, which means to me incredibly courageous, that you are leaving the official academics and going to the real world. That's an incredible example. I can see that it's the most concrete example of solidarity that I have seen in this conference. So this is very
so much, Fernando.
Incredible. Mirna, we wish you the best. And
Thank you.
I wanted just to follow up a little on Andres' comment. Your idea that knowledge is founded on science, science founded on mathematics, and mathematics founded on logic. That's an hypothesis which is a good way to begin. But even without that hypothesis, which I think we don't need to assume that hypothesis at all about foundations, your final conclusion about the pluralistic world is fundamental, and that can be done without the different layers of foundations. If mathematics without logic is already a plurality on her own, so that would be enough.
Indeed, I actually truly believe in what you said, Fernando. I had a wonderful experience going to India 2 times to conferences where I had a chance to listen to Indian historian of mathematics and how much they feel that their mathematics is existent and different, and it is not a mathematics that is based on the same logic that we have. So it is not something that came from the Greek tradition. Yet it is mathematics, and we have seen even in some recent examples, relatively recent for mathematical terms like Ramanujan, we have seen wonderful things that people doing this kind of thinking can contribute to all kind of mathematics. So there is a plurality of mathematics. Yet I have started with these assumptions because I think they are more commonly held than the opinion, which might be by some considered even heretic, that there is a plurality of mathematics. But that is the opinion that I have.
Can I ask a question?
Sure.
Hello?
Yes, go ahead.
Oh, okay.
Yes, George.
Yeah. Well, thank you. Thank you very much for your very challenging talk. I'm not sure I entirely agree with your conclusion. At least its status, I would say, is, from my point of view, is unproven. But I would like to perhaps query one of the methods by which you came to this conclusion, because you referred to the continuum hypothesis and the fact that we are unable to decide this on the basis of our notions about, our intuitions about set theory. But actually, the same turns out to apply to our intuitions about the natural numbers. Even those, even if we take a particular Diophantine equation, we cannot decide whether it has a solution in the natural numbers on the basis of our axioms, either even of set theory.
Indeed,
so,
yes, I know.
But does this actually mean that there is more than one model of the natural number, of what is true in the natural numbers? I don't think it does.
No, it just means that our axioms are not strong enough to understand what is true in the natural numbers.
Yeah.
It's our way of thinking. So I truly believe there is only one planet, and that there is only one set of people living on that planet, which is changing, of course, every second, people dying and being born. But I truly believe it is unique. But what I am saying is that our reasoning is not good enough to describe that model.
But that doesn't prove, for example, that we might not have, that we might not be able to formulate a notion of democracy, which incidentally, as I will try to show in my talk tomorrow, does not have to be anything remotely like what democracy has hitherto been assumed to be. But it doesn't seem to me to show that there could not exist a notion of democracy which could not work.
Well, I think it doesn't show much more than it shows that we do not have, that we will never have unique foundations of mathematics. Perhaps there are people who are still believing that we are going to find better axioms of set theory. In fact, there are some really good mathematicians, really important set theorists who believe in this. They're still searching for the axioms, the axioms. However, I think after you have tried 1 million times and you haven't succeeded, there is a lesson to take. And I think the same about this democracy. We have tried so many versions of imposing one view on everybody. Yes, we do not know that the version number 3,000,009 is not going to work, but I would rather that we do not make another 3 million wars which are going to bring us to that conclusion.
But there are certain truths. There are certain truths of mathematics which everyone accepts over the whole world. So even though they're merely axioms, so why should not the same be true of some future democratic organization?
Well, in the same way that it shouldn't be true of ultimate L, because to understand what ultimate L is, that some people are working on, you know, I'm talking about Wooden-Swig, it seems interesting, but it's ununderstandable. Because to develop such universal uniform models, one has to go through lengths which seem to be unnatural. Well, you know, I would love to if you were to prove me wrong. So I will look forward to your talk.
If I may, I want to make a short comment. Thank you, Mirna, for your talk. I know you, in a way, were addressing to us, no mathematicians, with a simple language to talk about complicated, your complicated field that we get lost when you use specific terms and specific language that we don't understand. So thank you for your talk. And I just wanted to congratulate you also for your initiative. I think it's a fantastic way of bringing abstract knowledge to the real world. And that's very political. So thank you for that initiative. I count on us on whatever we can, help or participate.
Thank you very much for your class.
It was a great pleasure.
So thank you.
Mirna, I just want to ask you another last mine at least question. And looking on during our university formation, we used to study the theory of the end of history. So I hope you read it, and that there are no other option. So I would like to ask you, how can we promote this solidarity applying graph methods and models? I hope you are hearing me.
Unfortunately, I didn't hear you from the end of history. That's when you mentioned end of history, then can you just say the rest?
How can we could apply the plurality of models to solidarity? Just for
I understand. You're asking how to apply this plurality to the society. Well, I think that was the question. Thank you, Esma. Excellent question. That was the question that I asked to Yogendra Yadav, because it seemed to me that he has thought of the answer. And I'm not sure I know the answer, but his answer was to do politics on the micro level. So do politics in small communities, and then maybe extend further, but really have everybody engaged. And well, I think this is not a bad idea. It reminded me of the times when everybody was supposed to be engaging in the cell of his, it was called Местная заедница. So something that, a small community around the block where people would be deciding things that are interesting for their own lives. I think that's a good model, and maybe that's how the plurality will work at the end. I don't know.
Another question? So thank you so much, Mirna. I think we will have a break now for a while, as I understand.
Yes, right, it's at 4 o'clock. No, 4:15 until 4:15, and then Esma, you have to leave afterwards, or did I understand?
Yes, I have to leave, unfortunately.
Okay, so because you will be leaving, I will pretend to be Esma, and I will be chairing the afternoon then. Yeah. Okay, thank you so much. Thank you. See you all.